In today's lecture, we will analyze the CRLH, that is Composite Right Left Hand Metamaterials. So there is a book, Electromagnetic Metamaterials, Transmission Line Theory and Microwave Application. This is written by Scalor. So in this book, at there is a chapter that is Transmission Line Theory and Metamaterials. So in this chapter, we can see real distributed one-dimensional CRLH structures. So at page number 119, there is a microstrip implementation of one-dimensional CRLH structure. So we switch on the 122 page number. Page number 123, you can see this is the CRLH transmission line, and it is fabricated using the interdigital capacitor. So these lines are showing the interdigital capacitance and shorted stub. This black strip is the shorted stub, and there is a via. So that is why it is shorted stub. So this via is connected to the ground. So in this lecture, we will develop a single unit cell of CRLH transmission line and do the analysis of it, and also plot the dispersion diagram. In this geometry, we have a section like this, and there is another section so here we can see that all these blue lines are conducting plates, and the white color in between these blue lines, it's a dielectric material. So when there is a combination of conducting plate and the dielectric material, it shows the behavior of capacitor. That is why this structure is interdigital capacitor. And here in this capacitance portion, they all are connected with the conducting wire. This wire will behave like inductor, and similarly there is a stub. It is also behave like a inductor. So this portion is inducting portion, and there is a via, which is also a conducting portion connected to the ground. So it makes the short circuit in between this plate and the ground plane. Now first we describe the CRLH metamaterial. So CRLH metamaterials are composite right left hand metamaterial, and there is a right hand and left hand wave propagation characteristics within a same unit cell. In a single unit cell, we have a right hand wave propagation and left hand wave propagation. CRLH metamaterials always made by interdigital capacitor, stub inductor, and microstrip transmission lines. Here, the left hand region supports the backward wave, and right hand region supports the forward wave. These forward waves are the same as conventional transmission line, but backward waves are found in the metamaterials, and the application of CRLH metamaterial are to design the leaky wave antenna. Now we can draw the equivalent circuit diagram. So here we have a capacitor, and there is one more capacitor. So by this pi circuit, we make the equivalent circuit diagram of this interdigital capacitance, and there is the inducting portion. So we can connect an inductor here. So first section is completed. Now this is connected again by this stub, and this stub is also shorted by this via, which is a conducting wire. So it's make the connection in between this stub line and the ground plane. So this can be represented by a T network. So here we have inductor and again one inductor, and there is some gap in between these lines. So we can connect a parallel capacitor at this point. So this represents one section. It is represented by pi network, and it is the another network which is represented by T network. Now it makes a two-port network, and the wave will propagate from this side to this side. And by this two-port network, we can easily calculate the S parameters, that is S11, S22, S21, and S12. So by calculating all these four parameters, we can do easily analysis of this unit cell. We have calculated the parameter of CRLH unit cell. Here you can see that unit cell period. This is single unit cell period, and it is repeating itself. So the period of single unit cell is 12.3 mm. This is initial design, and finally when after doing the optimization in HFSS, we got 11.4 mm. This structure is built up on the RT duroid dielectric material. So the substrate height of the dielectric material is 1.57 mm, and its permittivity is 2.2. So these two are the by default values. The radius of the VF, it is 0.12 mm. It is also by default value. This is calculated, and this is the optimized value. Stub length from this side to this side, it is 10 mm, and after calculating optimization, it is 10.9 mm. The stub width, this one, it is 1 mm. The interdigital finger length, this length, it is 10.2 mm, and the width is 0.3 mm, and the spacing in between two finger, this white portion, it is 0.2 mm. So we will develop the this architecture on HFSS software using this final design dimension. It is designed at 5 GHz frequency. Now we will simulate the design on HFSS software. So first we have to save this file as I am giving the name project 9, and do the initial settings. So in HFSS solution type should be model. Driven option should be network analysis. Then modeler units. Units are in mm. First, we will design the stub. So I am taking a rectangle from drawing box. The initial values are 0, 0, 0. On x-axis, here you can see that this is x-axis and this horizontal line is the y-axis. So this is the orientation of the figure. So on x-axis, I am taking the value of x is 10.9. This is the length of the stub, and the width of the stub is 1 mm. So it is 1 mm. Apply. OK. By clicking Control D, we can fix the geometry on the screen. Now I am rename it as stub, giving some color and apply some transparency. So this is our stub length. Now when you do the calculation of fingers, you will find that the fingers which are connected with the stub, the first finger is 0.5 mm apart from the top. Now see at the right bottom, coordinates are giving. So every time what I am plotting, see the coordinate at the bottom right. So the first finger is 0.5 mm from top. So here C at the x axis. So it is 0.234. Now this is 0.5. So the starting coordinates are at x axis 0.5, y and z should be 0. And then the width of the stub is 0.3 mm. So on x axis it is 0.3 mm, and on y axis its length is 10.2 mm. So this is in negative y direction. I am taking minus 10.2, and I am not applying any kind of thickness to the conducting portion. So it will remain 0. So here you can see these are the initial coordinates and these are the dimension of x and y. So again I am applying Control D. So this is my first finger which is attached with this step. I am giving name finger underscore stub, and providing some color and transparency. Now we have to draw 5 fingers. So first we will select it and then go on this along line, click it. Now where you will do the calculation that what is the distance between two fingers, you will find that they should be 1 mm apart from each other. So on x axis it should be 1 mm, and there is no change in y and z. So when I am clicking on enter, it will ask you how many duplicate lines you have to require. So we have to require 5 lines, 3, 4, 5. So these 5 fingers will generate. So these are the 5 fingers which is attached with the stubs. So just do the calculation. Just check, verify your calculation. So here at left block on measure data, you can see that this distance between two fingers is 0.7 mm, which is correct. Now we will apply the unite command. To make them single structure. So this is the unite. Now all these are connected with the stuff. Now we will design the next portion of the fingers. So they are 0.3 mm apart from this point on y-axis. So here initial point will be C at the bottom, 0. This will be minus 0.3 because the sorry 0.2 because the spacing between two elements is 0.2 and Z is 0. And the length will be 10.2 mm of each finger on dx. Dx is the thickness. The thickness will be 0.3 mm. And dy will be minus 10.2 mm and dz will be 0. So again I am giving name finger underscore line and giving the some color and transparency. Now this length of this finger is 10.2 and it is 0.2 mm apart from this stub or conducting portion. We have to require 5 fingers. So again click on this and apply the dimension. The dx will be 1 mm, dy will be 0, dz will be 0. So it takes automatically 5. Now you and finally we have to draw the uh, uh, a conducting plate which connects all these fingers. So the dimension of these conducting plate, this conducting plate will be on dx it is 4.8, on dy it will be minus 0.3, and dz it is 0. Now we will unite this second geometry. Select all element of second geometry and apply unite. We are renaming it as finger underscore length, giving some color and transparency. So this is our figure. Again see this diagram. So here you can see that all these are the unit cells, and at the starting point and at the end there are two ports are applied for the excitation. This is port 1 and this is port 2. So there are two ways to apply this excitation. The first, that you have to do the work, your all work in HFSS, or you have to switch on the HFSS 3D layout. So I am not switching on the HFSS 3D layout. I am doing all work on the HFSS. So the dimension of these ports are 5 by 5 mm. So I will just attach from this point. I have to again see at the bottom right 5 by 5. Okay, this is our first port. So I am giving the name port 1. I am providing some color and transparency. Similarly, this is again 5 by 5. This is port 2. So we will provide the excitation through this port. Now we will create the dielectric slab. So just create a box. Start it from -2 and on x-axis provide this dimension 14. We are giving actually some space at the edges of the unit cell on x-axis, and the thickness of the dielectric material is 1.57. This is by default value. Giving the name dielectric and apply the material. Those are RT Duroid 5870 trademark, giving some color and transparency. Now we will create the via. So we will select a cylinder from the drawing box. The radius of the via is 0.12 mm and thickness is same as the thickness of the dielectric slab. So it is minus 1.57 mm. So rename it and giving the name via and apply the material as copper. Now we have to subtract the this actually the material of the slab, this dielectric material and the copper thin wire via both are overlapping to each other. So we have to eliminate one. So just do copy of the via and again paste it, and now select dielectric slab and via and subtract. Now we make a cylindrical hole in the dielectric slab and then insert the conducting wire. So now it is perfect. Now we will provide the ground. So just select the box and apply this. Okay, giving the name ground. Provide some color. Now all these elements are unassigned. So port 1 and port 2. So for for finger 1, we will assign the boundary, finite conductivity, use material, and choose copper from project. Similarly, assign boundary, then provide finite conductivity, use material, copper, then ground, assign boundary, finite conductivity, use material, copper, and similarly for port 1 and port 2, we will apply the finite conductivity as copper. So here in this tree we can see that we have provided the conductivity to all the objects. Now we have to assign the excitation. So for assigning the excitation, this is XZ plane. So we just choose the rectangle, right click, assign excitation, then provide lump port. This is port 1 and the input impedance is 50 ohm. Assign new integration line, and this should be renormalize all modes. Full port impedance should be 50 ohm. Now for this port, again assign the excitation, lump port, now we will provide the boundary. So we will create the open region and the operating frequency is 4 gigahertz. So this open region is created. Now select this and we are making. Now we will apply the analysis. So in HFSS, analysis setup, add solution type, auto. This should be interpolating. The start frequency is from 1 gigahertz and frequency is 5 gigahertz. So now just see the check the validation. So all good. Now apply the analyze all. So it will take some time to run. After completing the execution, we will check the result. On the result, just right click and create model solution data report, rectangular plot in as parameter, choose S11, and on new report, we can see that this kind of graph, and it is resonant at uh, about 4.5 gigahertz supply marker, and it is 4.33 gigahertz. So the first step of this design is completed. Now we will plot the dispersion diagram. To plot the dispersion diagram, we will use the formula this one, beta p equal to cos inverse 1 minus S11 S22 plus S12 S21 divided by 2 times of S21. And for plotting the air line, we will use the formula 2 pi f multiply by LC plus S plus WS divided by 3 into 10 raised to power 8. Now for plotting the dispersion diagram, we will insert the formula in HFSS. So again, HFSS results, solution data report, rectangular report, and here you can see there is option output variable. Click on it and write the variable. First I am taking a variable beta, and in formula you have seen the expression for beta. So I am writing cos inverse. So here is the a cos is represent the cos inverse, and insert this. So a cos, or we can say cos inverse 1 minus S11. So I am writing 1 minus S11 multiply by S22. So taking multiply, put it here on none, S22, insert into expression. So it is a cos 1 minus S11 into S22, then plus S12 into S12 into S21. So this is cos inverse 1 minus S11 S22 plus S12 S21. And this whole term is divided by 2 times of S21. So I will multiply this term, divided this term by 2 times of S21. Now it is complete expression for beta. Just add. So we have add the beta. Now we have to also plot the airline. So for plotting the airline, we need some parameters. So I'm just entering some parameter. So first variable is frequency. So here frequency, select variable, frequency is here. Insert F frequency, we add the frequency. Then LC, the value of LC is 10.2 mm. Then next value is spacing. So I am taking G as a space in between two finger, and its value was 0.2 mm. The next value is WS, that is the width of the stub, and it was 1 mm. So we have add all these values. Now I am taking the expression airline, and in this expression this is 2 pi f, and the whole term will multiply with LC plus G plus Ws. And this whole term is divided by 3 into 10 raised to power 8. So this term will be divided by 3e8. Now this is all done. Now we will plot the dispersion diagram. So on HFSS results, rectangular plot, and here solution output variable, and we have beta, and we will take the real value of beta here. This is beta, and we will take the real value of beta and just generate the report. Now we will add the plot the airline. So just add trace airline, apply trace. So here this is our dispersion diagram, and here you can see that the phases are repeated. So after each cell the phase are repeating to itself, so it shows that diagram is correct, and this linear line is also show that airline is also correct. Now somewhere you will see that this curve is in vertical form. So to convert this in vertical form, what you will do, just go on the result. I am directly switching on this result, and on x-axis in output variable I will plot beta, a real value, and on y-axis I will plot f. So when I click on new report, you can see that this kind of diagram you will found in the books. And similarly, to add airline, here select the airline, and on y-axis keep f as it is. So here you can see this airline is plotted. So now add trace, and we will add the beta, real value of beta, apply trace. So this is the value. This is approximately 1.3 to 1.8 gigahertz frequency band. It is the value of beta will be 0. So by this diagram you can see this is the reason for the fast wave, because beta is less than k naught for this reason, and this green region is for the slow wave region where beta is greater than k naught, and this is the airline. So this is all about the interdigital capacitance unit cell, including stub and via, and you also seen the dispersion diagram, how to plot dispersion diagram, and how to analyze the value of beta, and how to insert the formula in HFSS. Thank you.